Good evening, ladies and gentlemen. Welcome to our final topic that we'll be covering on this YouTube course, at least this part of YouTube course, which will be generalized linear models, which is one of the most important aspects of general statistical modeling, as GLMs are extension of classical linear models, allowing structural creation of all types of models. This is something that is really not much new since our previous lectures, but we will show how certain aspects can be modeled and how such models are structured. So, generally, linear models are simple, and unfortunately, it's not exactly everything that we need, because linear models are based on usually normal distributions, where we, instead of fitting one normal distribution that will fit our measurements, we use normal distribution with means that are parameterized by our predictors. So we create such model that will connect our predictor variables as a linear combination of predictor variables and certain intercept coefficient in order to synthesize a new mean, and this mean will be used for our modeling. This is a simple situation, and in most cases even solvable analytically as a solution of certain system of equations. However, this approach is not enough. Of course, we might want to expand our concept outside of normal distributions, for example, by using student's t-distribution, which is, as we've seen in the one of the earlier lectures with Newcomb's data, it is more robust toward outliers. So because it has thicker tails, it allows that certain samples can be far away from the bulk of them, and it will not influence our inference. And that case is still simple. We still have to find the parameter mi that is for each of the mi I for each of outputs, which is connected to certain values of predictors, and everything is nice. However, here we don't have analytical solutions usually anymore, and we'll have some problems to compute those. That's when our Monte Carlo apparatus comes in and allows us more computation. However, real numbers are not always enough. If our data has a form of integers, then representing them as real numbers might be a bit problematic. It will not lead us to right results. We'll get fractions where there shouldn't be any fractions. So generally there will be a problem with such situation with continuity of such problems. Fortunately, we have some distributions that are generating for us integer values. For example, for binary results, we have binary distribution. For sequence of binary results, we have binomial distribution, which is generally a multiple execution of Bernoulli trials. For integers, we have Poisson distributions and variants of those, like negative binomial distributions. And also we have some zero constraint distributions, so distributions that, for example, limit the values only to the positives, like exponential or gamma or log normal. So there exists certain distributions that give us possibility to handle something that is not necessarily a real number. If we want to full constraints of parameters, then maybe we could use some kind of constraint transformation. So let's focus on integers. In integers, like for example, a Bernoulli distribution, we just switched likelihood. If we had previous likelihood with normal, we just replaced mi with a linear combination of predictors. So maybe we could do it with Bernoulli distributions, just replace our theta e with linear combination of predictors. While linear, again, as we said before, Taylor expansion, every model can be at least locally approximated by linears. Unfortunately, this is wrong. Why? Because parameters for integer value distribution are constrained. For example, for binomial and Bernoulli distributions, we have probabilities. And probabilities are constrained to 0-1 interval, and we can't do anything about it. For Poisson distribution, we have the rate parameter, which is greater than with a real number greater than 0, which is again constraint parameter. And the linear combination of predictors is in general unbounded because first of all our predictors can get arbitrarily large values and the parameters can get arbitrarily large values, and then we get something that will be unbounded. Even if our predictors are bounded, then still we have the problem of number of the coefficients, and even if those will be bounded, then again will be a problem that we will have there might be an unfortunate combination that that for example we have all xi's are bounded to 1 and all our betas are bounded to 1, but there is a combination that all betas are equal to 1, x's are equal to 1, and then with large betas we'll go outside of 0, 1. So such situation is very problematic, and constraining the actual combination of alpha plus beta xi is not an option, because for computational reasons we will need as smooth functions as possible, because all our computations are based on derivative approximations, and using derivatives requires smoothness on those functions. If there are enough, if we introduce constraints, then we get a sharp cuts of our functions, and that will be computationally very difficult to analyze. That's why we don't want to do that. So let us focus on different options, and for these options are so-called link functions. Link functions is where the generalized in GLMs come from, because we use still our linear combination of predictors, but those predictors, this linear combination will be a value of certain link function of parameter theta, and this parameter theta is used in the distribution. So in other words, the likelihood of Iy is distributed with a parameter equals f to minus 1, so inverse of f, times of the predictor combination value. So our function f will be of course an invertible function of taking us from real numbers into the actually the f to minus 1 function takes us from real numbers to the certain interval that is a distribution dependent constraint. And of course there are multiple examples how such situations are constructed. First of all is the exponential or logarithmic link. It is a situation when we have positively constrained parameters, especially in Poisson distribution. In Poisson distribution, lambda has to be positive, so for each combination of predictors, lambda I also has to be positive. And one function that can guarantee us such situation is the exponential function. Exponential function has the advantage of being smooth and generally taking away the negative values of alpha plus beta xi, which are being shrinked down to 0 very, very fast. In such situation, our Poisson model would be constructed as yi is distributed as Poisson with coefficient lambda I, and logarithm of lambda I is equal to our linear combination of predictors. So this is the logarithmic approach for a logarithmic link function. In case of binary values, the most popular approach is so-called Logit function, or a Logit link, which leads us to so-called a logistic regression. It is based on so-called logistic function, also called Logit, which is a logarithm of its argument divided by 1 minus that argument. If the argument is constrained from 0, 1, this function, it corresponds to minus plus infinity interval. So our function will get us through, our function will allow us to transform our results from real values of alpha plus beta xi into a 0,1 interval for theta. So our unbounded combination of predictors will lead us to bounded coefficients. How does it work? It works like this, that there is almost linearity in the middle of around 0 of this function, which is then becomes more and more saturated as we go away from 0. So generally we get a shrinkage from both sides of the coefficient values, from negative and positives, which will fit us between 0 and 1. The alternative to Logit function is a probit function, and probit is a bit more complicated because it's based on the cumulative distribution function of normal distribution, which is so-called error function, which is just a kind of complicated integral which does not have an analytic value, but it is practically computed in many situations. The probit regression uses the fact that cumulative distribution function corresponds from takes values from minus to plus infinity and assigns them probability from 0 to 1. In case is a situation, we could use an inverse of cumulative distributive function, which is the probit function, and use it as a link function. In this case, we will get again transformed from unbounded domain into the bounded domain of 0 to 1. And the main difference between probit and logit function is in the tails, because probit function is faster at squeezing values to 0 or to 1, because its tails are much lighter than in case of probit or in case of logit function. And these are the main basics for creation of generalized linear models. We'll now go to some examples that will allow us to understand the concept better, starting from prior assignment through the prior predictive checks, and then to getting some inference and potential model tuning. And this will be in a second part